There's something haunting about the way the Earth tells its stories, not in words, but in layers of stone, in twisted rock formations, and in the silent scars left by unimaginable forces. Picture this: you're standing at the edge of the Grand Canyon, where the walls stretch down for miles, each stripe of color a chapter in a billion-year-old saga. But these aren't just pretty patterns, they're cryptic messages etched by disasters so colossal they reshaped continents, wiped out entire species, and reset the clock of life itself. Today, we're going to crack that code. Hidden within Earth's geology are 30 astonishing clues, each one a piece of a puzzle that reveals past global catastrophes, from asteroid strikes that darkened the sky to volcanic eruptions that drowned the land in fire. And here's the thing, these aren't just tales of the distant past. They're warnings, blueprints, even survival guides for our future. Think about the last time you held a fossil in your hand. That tiny shell or leaf imprint isn't just a relic. It's a snapshot of a world that vanished in an instant. Now, scale that up. Imagine entire mountainsides littered with the bones of creatures that thrived one day and were erased the next. What caused these mass extinctions? How did the planet recover? The answers are buried in plain sight, written in the language of rock and sediment. From the eerie iridium layers that betray an asteroid's deadly kiss to the ripple marks left by ancient tsunamis, Earth's geology is a detective story waiting to be solved. And the stakes couldn't be higher, because if we can read these messages, we might just predict or even prevent the next great catastrophe. This isn't just a journey through time. It's a voyage into the very heart of what makes our planet alive, dynamic, and sometimes terrifying. We'll travel to sites where the ground still bears the wounds of ancient violence, where scientists are piecing together clues like detectives at a crime scene. You'll see how a single layer of ash can rewrite history, how a crack in the ocean floor can trigger global chaos, and how the same forces that once devastated life also paved the way for our existence. So, are you ready to step into the field and become a geological sleuth? Because the Earth has been keeping secrets, and it's time we listened. Let's start with the first clue, a layer of dust so thin you could miss it with the naked eye, yet so packed with meaning it rewrote our understanding of Earth's history. In the late 1970s, geologist Walter Alvarez and his team were studying a peculiar stripe of clay in Italy when they stumbled on something extraordinary. This unassuming layer, no thicker than a pencil line, was laced with iridium, a metal so rare on Earth's surface it might as well be a cosmic visitor. And that's exactly what it was. Iridium thrives in asteroids and comets, but here on our planet, it's mostly buried deep in the mantle. So how did it end up scattered evenly across the globe, sandwiched between layers of rock like a sinister bookmark? The answer lies in a catastrophe of unimaginable scale. 66 million years ago, a mountain-sized asteroid, perhaps 6 miles wide, screamed through the atmosphere and slammed into what's now the Yucatan Peninsula. The impact unleashed energy equivalent to billions of atomic bombs, vaporizing rock, triggering wildfires across continents, and hurling enough debris into the sky to blot out the sun for years. The iridium layer is the asteroid's calling card, a sooty fingerprint left in the geologic record. But here's what's chilling. This wasn't just a bad day for dinosaurs. It was a reset button for life itself. The fallout acidified the oceans, collapsed food chains, and wiped out 75% of all species. And yet, without this disaster, mammals might never have gotten their chance to rise. Now peer closer at that iridium layer, and you'll find more than just a story of destruction. It's a measuring stick for time. Above it, the fossils change dramatically. No more towering reptiles, just smaller, scrappier survivors. Below it, the world is frozen in a snapshot of a lush, ancient ecosystem. This single stripe of clay is like a geological pivot point, separating two entirely different versions of Earth. But the real question isn't just what happened, it's could it happen again? Astronomers track near-Earth objects, and while another dinosaur killer isn't imminent, smaller impacts are a real threat. The Iridium layer doesn't just whisper about the past, it shouts a warning for the future. What's astonishing is how delicate this evidence is. Wind or rain could have erased it. Yet here it is, preserved with eerie precision, as if the Earth itself wanted us to find it. And that's the beauty of geology, it's patient. The rocks remember what we've forgotten, holding onto truths until we're ready to listen. So the next time you see a cliff face or a canyon wall, look closer. Those stripes aren't just pretty, they're pages in the greatest thriller ever written. And we've only just begun to read. Now, let's zoom way in, to a mineral so ordinary you've probably walked right over it without a second thought. Quartz, that glittering speck in granite countertops and sandy beaches, holds a dark secret. Under the right microscope, some of these crystals reveal a labyrinth of microscopic fractures, like a pane of glass shattered by an invisible hammer. But this isn't just any damage. These are shocked quartz grains, deformed under pressures so extreme they could only come from one thing: an asteroid slamming into Earth at tens of thousands of miles per hour. Take the Sudbury Basin in Canada, a sprawling, crater-shaped scar older than dinosaurs. Here, shocked quartz litters the ground like confetti from an ancient cosmic party. The fractures inside these crystals, called planar deformation features, are like a fingerprint of violence. They form when shock waves from an impact ripple through the crust, squeezing rock with more force than Earth's own tectonic plates ever could. And here's what's wild: these tiny fractures don't heal. They stay frozen in time, a permanent record of the moment the sky fell. But Sudbury isn't alone. Shocked quartz has been found at dozens of impact sites worldwide, from the Vredefort crater in South Africa to the dusty plains of Meteor Crater in Arizona. Each discovery tells the same story: a split second of chaos preserved for eons, and the more we find, the clearer it becomes Earth's history is pockmarked with these cataclysms. Some researchers even argue that major impacts might happen every few million years, far more often than we'd like to believe. What's even more startling is what these crystals don't show. Volcanic eruptions and earthquakes can twist and melt rock, but they rarely create the precise, parallel fractures of shocked quartz. That uniqueness makes these grains like forensic evidence in a planetary crime scene. By mapping their distribution, scientists can trace the fallout from impacts, reconstructing how debris rained down across continents. In some cases, shocked quartz has even helped pinpoint long eroded craters, revealing catastrophes we didn't know existed. Then there's the bigger question lurking in these fractured crystals. What else did these impacts trigger? An asteroid strike doesn't just leave a hole, it can ignite wildfires, unleash tsunamis, and pump enough dust into the atmosphere to plunge the planet into a years-long winter. Shocked quartz might be the smoking gun, but it's part of a much larger story of ecological collapse and rebirth. And here's the kicker: while we've gotten better at spotting these microscopic clues, there are almost certainly more hidden in plain sight, waiting to rewrite history again. So the next time you pick up a pebble, remember, it might not be just a rock. It could be a time capsule, a witness to one of Earth's most violent days. And as we keep searching, these tiny fractures might just crack open secrets we never saw coming. Imagine standing in a field after a storm, picking up smooth, glassy pebbles scattered across the ground. But this isn't ordinary glass, it's tektites, nature's own meteorite jewelry, forged in the heart of planetary catastrophe. These tiny, tear-shaped beads aren't crafted by human hands or volcanic fires. They're the remnants of asteroid impacts so violent they turned solid rock into vapor, hurling it miles into the atmosphere where it cooled and hardened into glass before raining back down. From the lush jungles of Southeast Asia to the rolling hills of Central Europe, tektites are Earth's way of tattooing its skin with the memory of cosmic collisions. Take the Australasian strewn field, a vast tektite blanket stretching from Madagascar to Australia, covering nearly a third of the planet's surface. The sheer scale is mind-boggling. These glass droplets didn't fall gently. They were the aftermath of an impact so powerful it scattered debris across oceans and continents. Scientists traced their chemical fingerprints to a single, cataclysmic event around 790,000 years ago, though the crater itself remains elusive, hidden beneath shifting tectonic plates or eroded by time. What's chilling is that this wasn't a dinosaur killer-sized disaster. It was smaller, yet still capable of global fallout. Now hold a tektite in your palm, and you're holding a snapshot of apocalypse. Their surfaces tell stories. Some are pitted like golf balls from screaming through the atmosphere, others polished smooth by millennia of wind and water. But the real magic is inside. Slice one open, and you'll find swirling bands, evidence of molten rock spinning mid-air like cosmic taffy. Some even contain microscopic bubbles, tiny time capsules of Earth's ancient atmosphere trapped in the moment of impact. These aren't just rocks, they're forensic evidence of a planet under siege. What's even more startling is how fast tektites form. In less than a minute, a mountain's worth of rock can vaporize, launch into space, and freeze into glass before hitting the ground. That speed locks in clues about the impact's angle, force, and even the type of rock it obliterated. For geologists, tektites are like reading a disaster's diary written in molten ink. And their distribution is a roadmap of devastation. The farther you travel from an impact site, the smaller and more scattered the tektites become, like breadcrumbs leading back to ground zero. But here's the haunting part. If a similar strike happened today, tektites would be the least of our worries. The initial blast would flatten cities, the heat wave would ignite continents, and the debris cloud could trigger a years-long winter, collapsing agriculture. Tektites are beautiful, yes, but they're also a stark reminder of how fragile our civilization is in the face of Earth's volatile history. Yet there's hope in these glassy messengers, too. By studying them, we've learned to predict the fallout of future impacts where debris would land, how climates might shift, even which regions would become uninhabitable. Tektites are more than relics, they're teachers, and as we piece together their scattered lessons, we're not just uncovering the past, we're rehearsing for survival. So the next time you hear about a shooting star, remember, the real magic isn't in the streak of light. It's in the fragments left behind, glass raindrops from the sky, whispering warnings from a time when the world burned. And if we listen closely, they might just help us dodge the next cosmic bullet. Beneath the quiet surface of ancient rock layers lies one of Earth's most terrifying chapters, a thin, unassuming stripe that marks the closest life ever came to total annihilation. 252 million years ago, at the boundary between the Permian and Triassic periods, something went horribly wrong. Over 90% of all species vanished. Not just dinosaurs, but entire ecosystems collapsed in what scientists call the Great Dying. This wasn't a slow decline. It was a planetary massacre, etched into stone from China to Greenland, where fossil records abruptly switch from teeming diversity to eerie silence. The smoking gun, a vast volcanic nightmare known as the Siberian Traps. Picture an eruption so colossal it didn't just spew lava, it cracked the Earth's crust open like an egg, unleashing millions of cubic miles of molten rock over hundreds of thousands of years. But the lava was just the beginning. These eruptions pumped unimaginable amounts of carbon dioxide and methane into the atmosphere, turning the planet into a pressure cooker. Temperatures soared, oceans acidified, and oxygen levels plummeted until even the hardiest creatures gasped for survival. The rocks from this period tell the tale, layers of stagnant, lifeless sediment, stained with minerals that only form in toxic, oxygen-starved waters. What's truly unsettling are the parallels to today. The Siberian Traps didn't just heat the planet, they rewired it. Sound familiar? Modern climate change isn't happening on the same scale, but the mechanisms are eerily similar. Greenhouse gases spiking, oceans turning acidic, and ecosystems buckling under the strain. Back then, it took life nearly 10 million years to recover. The fossils above the extinction layer are a ghost town, just a handful of scrappy survivors, like the humble Lystrosaurus, a pig-sized reptile that somehow outlasted the apocalypse and dominated the empty world left behind. But here's the twist: the Great Dying wasn't just heat and poison. It was a cascade of disasters, each amplifying the next. As temperatures rose, methane, a greenhouse gas 25 times more potent than carbon dioxide, bubbled up from thawing seafloors, turbocharging the warming. Meanwhile, the acidified oceans became hostile to shell-building creatures, collapsing food chains from the bottom up. Even the soil died as acid rain leached away nutrients, leaving behind barren wastelands. This wasn't a single catastrophe, it was a domino effect where one disaster triggered another until the planet became almost unrecognizable. Now, zoom in on those Permian-Triassic rocks, and you'll find something even more haunting: fungal spikes. Right after the extinction, fossil layers are packed with fungal spores, nature's cleanup crew, thriving on the rotting remains of a dead world. It's as if Earth itself was in mourning, covered in a shroud of decomposers. But these spores are also a sign of hope. Life didn't give up, it adapted, evolved, and eventually clawed its way back. The question is, will we learn from this ancient warning? Because the Great Dying wasn't just bad luck, it was a blueprint for how a planet can tip over the edge. Today, we're not facing Siberian-scale eruptions, but we are pumping carbon into the atmosphere at a rate that would make those volcanoes blush. The rocks from the Permian-Triassic boundary aren't just relics, they're a mirror. And if we don't like what we see, it's not too late to look away. The Earth's memory is long, but its patience isn't infinite. The next chapter, that's still ours to write. Walking through the desert of the American Southwest, you wouldn't expect to find traces of an ocean, let alone the aftermath of a tsunami powerful enough to rewrite coastlines. Yet embedded in the sandstone of places like Utah and Arizona are wave patterns so enormous they defy belief. These aren't gentle ripples from a passing breeze. They're fossilized tsunamis frozen in stone for 300 million years, each crest and trough stretching hundreds of feet apart. To stand beside them is to stand beside the ghost of a catastrophe, a moment when the ocean didn't just rise, it roared. How does a tsunami leave its mark on solid rock? Picture a wave so colossal it drags boulders the size of houses across the seafloor, carving grooves into the sand like a giant's fingernails. As the water retreats, it leaves behind a chaotic mess of sediment churned, twisted, and piled into unnatural shapes. Normally, tides and currents would erase this chaos in days. But in rare moments, another disaster strikes first. A sudden burial under volcanic ash or a landslide that seals the seabed in an airtight tomb. Over millennia, pressure turns that buried turmoil into stone, preserving the tsunami's fury like a fossilized scream. The scale of these ripples is what chills geologists. Modern tsunamis might leave wave marks a few feet apart. the ancient ripples in the southwest. Some measure over 50 feet from crest to crest, suggesting waves taller than skyscrapers. What could generate such power? One theory points to underwater landslides, continental shelves collapsing like a trapdoor, displacing enough water to drown continents. Another points to the cosmos, a meteor slamming into the ocean, unleashing a splash of liquid rock and steam that circled the globe. Either scenario would have been apocalyptic, flooding entire regions in minutes and leaving nothing but these eerie ripples as a tombstone. Now fast forward to today. Coastal megacities like Tokyo, Mumbai, and New York perch at the edge of rising seas, shielded by concrete barriers designed for storms, not planet-altering floods. The fossilized tsunamis whisper a warning. Our defenses are built for the disasters we've seen, not the ones Earth has proven it can unleash. In 2004, the Indian Ocean tsunami killed over 200,000 people with waves a fraction of the size implied by these ancient ripples. If a similar event struck today, even the most advanced early warning systems might offer only minutes to flee. But here's the twist: these ripples aren't just doom-laden prophecies. They're teaching tools. By studying their spacing and shape, scientists can reverse engineer the tsunamis that made them, calculating their speed, depth, and even the angle of impact. That knowledge isn't just about the past, it's a blueprint for survival. Engineers are already designing tsunami-proof buildings with breakaway walls and elevated escape routes, inspired by the very forces that once scoured these deserts. The real lesson of these stone waves isn't that disaster is inevitable. It's that Earth has a memory, and it's willing to share its secrets if we're brave enough to listen. Because while we can't stop tsunamis, we can learn from the scars they leave behind. And sometimes the difference between survival and oblivion is written in the ripples. One of Earth's most chilling geologic mysteries lies buried in a thin layer of sediment barely thicker than a coin. Around 12,800 years ago, the planet was warming steadily, glaciers retreating, forests creeping north, until suddenly, without warning, everything reversed. Temperatures plummeted, ice sheets surged, and the world snapped back into a deep freeze for over 1,000 years. This bizarre climate U-turn, called the Younger Dryas event, left behind a trail of cryptic debris, microscopic diamonds forged in fire, tiny glass beads born from molten rock, and a black mat of carbon-rich soil that blankets fossils of extinct giants like mammoths and saber-toothed cats. What could flip the planet's thermostat so violently? The answer might rewrite human history. Dig into those Younger Dryas sediments, and you'll find something that shouldn't be there: nanodiamonds. These aren't the glittering gems of jewelry stores. They're microscopic crystals with a structure so unique they only form under extreme pressure and heat, like the kind generated by a comet exploding in the atmosphere. Mixed with these diamonds are melted spherules, tiny orbs of glass that rain down like scorching hail. Together, they paint a picture of a cosmic catastrophe, a fragmented comet or asteroid detonating over North America, igniting wildfires across continents and hurling enough dust into the sky to block sunlight for generations. The climate didn't just change, it was punched. But the real shock isn't just the event itself, it's the aftermath. The Younger Dryas boundary marks a mass grave for Ice Age megafauna. Bones of mammoths, giant sloths, and dire wolves pile up beneath that dark layer, as if something flicked a switch on their world. Human cultures collapsed too. The Clovis people, once thriving with advanced stone tools, vanished almost overnight. Some researchers think survivors fled south, their migration patterns scrambled by ecological chaos. It's as if the comet didn't just alter the climate, it rerouted the course of civilization. Now, here's the unsettling part. Earth's climate isn't a dimmer switch. It's a seesaw capable of tipping from one extreme to another with terrifying speed. The Younger Dryas proves it. Ice cores from Greenland show temperatures in the northern hemisphere dropped by up to 15 degrees Fahrenheit in decades, a blink in geologic time. And while the comet theory is still debated, the evidence is mounting. From Carolina Bay's mysterious elliptical depressions that might be impact scars, to platinum-rich layers found as far away as South Africa, the clues suggest a global catastrophe. What's haunting is how many similar climate switches might be hidden in the rocks. The geologic record is littered with abrupt shifts, sudden warmings, freezes, and methane burps that science is only beginning to decode. If the Younger Dryas teaches us anything, it's that Earth's climate is more fragile than we thought, capable of flipping from stability to chaos with the nudge of a cosmic visitor, or perhaps human activity. So the next time you hear about climate change as a slow, gradual process, remember the Younger Dryas. The planet doesn't always move at a crawl. Sometimes it leaps, and the scars it leaves behind are warnings written in diamonds, glass, and bones. The question isn't just what happened 12,000 years ago. It's whether we're standing on another threshold, one we might not see until it's too late. Deep in the rust-red cliffs of Western Australia's Hamersley Range, Earth keeps one of its oldest and most paradoxical secrets: banded iron formations. These striking striped rocks, with their rhythmic layers of iron oxide and silica, look almost like a barcode from the distant past. But this isn't just pretty geology. It's the fossilized aftermath of a planetary-scale crisis, a time when life itself poisoned the world. 2.5 billion years ago, Earth's oceans were thick with dissolved iron, a relic of the planet's volcanic infancy. Then something revolutionary happened. Cyanobacteria, the earliest photosynthetic organisms, began exhaling oxygen as waste. To us, oxygen means life. But to the ancient microbes thriving in that primordial soup, it was toxic. Imagine an entire planet rusting from the inside out. As cyanobacteria multiplied, their oxygen waste reacted violently with the iron in the oceans, binding into iron oxide rust that sank to the seafloor in thick, alternating layers. These banded formations are the geologic equivalent of a chemical battleground, each stripe marking another surge in oxygen production. But the real tragedy unfolded for the anaerobic organisms that had dominated Earth for eons. To them, oxygen wasn't just pollution, it was a death sentence. This was the Great Oxygenation Event, the first mass extinction in Earth's history, and it was caused entirely by the success of another life form. What's chilling is how slow the disaster unfolded. The rusting oceans locked away oxygen for millions of years, buying time for anaerobes to retreat into isolated pockets like deep sea vents or underground sediments. But eventually, the atmosphere tipped, oxygen levels soared, and Earth's chemistry changed forever. The banded iron formation stopped forming abruptly, not because the iron ran out, but because all the free iron had been used up, rusted into oblivion. The planet's oceans, once murky green with dissolved metal, turned clear. The sky, once hazy with methane, turned blue. Life had terraformed its own home and paid a brutal price. Yet without this catastrophe, complex life as we know it might never have emerged. Oxygen's corrosive power didn't just kill, it unlocked new energy pathways, paving the way for larger, more active organisms. The same poison that wiped out Earth's first inhabitants became the foundation for everything that followed. There's a profound lesson here: progress isn't always gentle. Evolution isn't a straight line. Sometimes the very mechanisms that sustain one era are the wrecking balls of another. Today, banded iron formations are more than just geologic curiosities. They're mirrors. As we pump greenhouse gases into the atmosphere and acidify the oceans, we're repeating that ancient story, not with oxygen, but with carbon. The cyanobacteria didn't intend to destroy their world. They were just surviving. Sound familiar? The rocks whisper a warning. Life reshapes planets, but rarely with foresight. The question is, will we learn from their scars or become the next stripe in Earth's geologic record? India's Deccan Traps don't look like a crime scene at first glance. These sprawling plateaus of basalt, some layers over a mile thick, resemble a quiet, weathered landscape, more like a giant staircase than the aftermath of apocalypse. But peel back the layers, and you'll uncover a volcanic fury so vast it makes Mount Vesuvius look like a campfire. 66 million years ago, these plains weren't quiet. They were a battleground where Earth's crust split open like a wound, gushing enough lava to bury continents. And here's the chilling part. This eruption didn't just happen to coincide with the dinosaurs' demise. It may have helped kill them. Picture a volcanic outburst so relentless it lasted hundreds of thousands of years. The Deccan Traps didn't explode in a single dramatic blast. They oozed, a slow-motion disaster that flooded an area the size of Texas with molten rock. But the lava was just the opening act. The real devastation came from the gases sulfur dioxide, carbon dioxide, chlorine pumped into the atmosphere in amounts that dwarf modern human industry. Acid rain scorched vegetation, turning lush forests into skeletal remains. Skies darkened not for months, but for generations, as aerosols reflected sunlight back into space, triggering global cooling. The fossil record tells the tale. Layers of pollen vanish abruptly, replaced by spores from ferns, nature's first responders to ecological ruin. Yet amid this chaos, life clung on. Crocodiles, turtles, even early mammals weathered the storm. Why them? The traps hold clues. Unlike dinosaurs, which were often large, specialized, and dependent on stable ecosystems, survivors shared key traits: small size, adaptable diets, and the ability to burrow or hide in water. Freshwater ecosystems, buffered from acid rain by minerals in rivers, became lifeboats. Meanwhile, species that could endure starvation, like crocodiles, which can go months without food, outlasted predators that needed daily meals. The Deccan Traps aren't just a monument to destruction. They're a survival guide etched in stone. Now, fast forward to today. The traps' ancient gases mirror our own pollution crisis: carbon emissions spiking, oceans acidifying, forests burning. But there's a crucial difference. The Deccan eruptions were unstoppable. We have a choice. By studying how life navigated that ancient catastrophe, we're not just unearthing the past. We're decoding strategies for resilience. Could underground seed banks like those built in Norway today mimic the burrowing survivors of the traps? Could rewilding wetlands create modern refuges, just as rivers once sheltered turtles? The most haunting lesson, though, isn't about survival, it's about time. The Deccan Traps didn't kill quickly. They eroded ecosystems over millennia, giving life just enough room to adapt. Today's changes are happening 1,000 times faster. The traps whisper a warning. Resilience isn't infinite, but they also offer hope. Life has faced worse and endured. The question is, will we learn from those who outlasted the flood, or become fossils in the next layer of stone? Buried beneath Greenland's endless ice sheets lie frozen time capsules, each one holding a breath of ancient air, some untouched for nearly 1 million years. These ice cores, painstakingly drilled from depths of over 2 miles, are more than just columns of compacted snow. They're Earth's climate diaries, written in bubbles of trapped gas and layers of dust. And when scientists crack them open, the story they tell is anything but gentle. Hidden in these pristine cores are sudden, jagged spikes of methane and carbon dioxide chemical screams from a planet caught in the throes of violent change. Take the Dansgaard-Easter events, for example. These abrupt warming periods recorded in Greenland's ice showed temperatures rocketing upward by as much as 15 degrees Fahrenheit in decades. Not centuries, decades. How the bubbles reveal the culprit. Greenhouse gases surging in perfect lockstep with the warming. Methane, released from thawing permafrost and bubbling wetlands, acted like a turbocharger, amplifying the heat and pushing the climate past tipping points we're only beginning to understand. And here's what's terrifying. These weren't isolated flukes. They happened over and over, like a record skipping on the same nightmare track. But the real shock isn't just the speed of these shifts, it's how familiar they feel. The same gases driving ancient warming are now spiking again, this time from human hands. The ice cores don't just whisper about the past, they hum with eerie parallels. When researchers compare the methane levels from pre-industrial air trapped in ice from the 1800s to today's atmosphere, the graph doesn't curve. It jumps, and while natural spikes took centuries to unfold, we've replicated them in a fraction of the time. The ice is screaming a warning we've heard before, just never this loud. Then there's the dust. Layers of fine particles preserved between ice bands tell another side of the story. During cold snaps, the cores show thicker dust deposits, evidence of dried-up lakes and relentless winds scouring barren landscapes. But when warming hit, the dust vanished, replaced by cleaner ice as rains returned and vegetation regrew. It's a pattern we're seeing again today, as droughts expand and fertile soils turn to powder. The difference this time, the dust isn't just a consequence. It's a feedback loop, darkening ice sheets and accelerating melt by absorbing more heat. What's haunting is how delicate this evidence is. A single warm summer can erase centuries of climate data if the surface melts. Yet against all odds, these frozen archives survived, waiting for us to listen. And the lesson they offer isn't subtle. Climate change isn't a distant theory. It's a recurring plotline in Earth's history, written in gas and ice. The question isn't whether the planet can handle another spike. It's whether we can, because the ice cores don't just record disasters. They catalog recoveries, slow, grinding rebounds that took millennia. Humanity doesn't have that kind of time. So the next time you hear about greenhouse gases, remember those tiny bubbles trapped under miles of ice. They're not just relics, they're prophecies. And if we ignore them, we're not just repeating history, we're racing toward a chapter even the ice hasn't seen. Stretching from New Jersey to Florida, the Carolina Bays form one of Earth's most haunting landscapes, a sprawling field of 500,000 elliptical depressions, each one perfectly shaped like a teardrop frozen in time. From the air, they look deliberate, as if some giant hand pressed thumbprints into the soft earth. Ranging from mere ponds to basins over a mile long, these enigmatic craters all share an eerie consistency. Their long axes point unwaveringly toward the Great Lakes and Canada, like compass needles locked onto some invisible north. For decades, scientists scratched their heads. How could wetlands so orderly form naturally? The answer might rewrite our understanding of catastrophe. One theory ties these bays to the same cosmic violence that triggered the Younger Dryas freeze. Imagine a fragmented comet or asteroid, hurtling toward Earth at an oblique angle, exploding in a series of airbursts over what's now the Atlantic. The shockwaves would have scoured the ground like a blowtorch, vaporizing soil and water in an instant, leaving behind these scorched hollows. Supporting this idea are microscopic clues, platinum spikes and nanodiamonds found in bay sediments, telltale signatures of extraterrestrial impact. Even the bay's alignment fits. Their northwest-southeast orientation matches the trajectory of a proposed impactor coming from the northeast. their shapes sculpted by the angle of the blast. But not everyone's convinced. Skeptics argue the bays could be the work of wind and water, ancient whirlpools or sinkholes carved during Ice Age floods. Yet this doesn't explain their uniformity. Natural erosion rarely creates 500,000 near-identical formations, all facing the same direction. Even more puzzling are the bays' raised rims, packed with sand so pure it's mined for industrial use. These aren't gentle slopes, they're abrupt ridges, as if material was flung outward and frozen mid-flight. The real mystery isn't just how the bays formed, it's what they erased. Indigenous oral histories speak of a time when the sky fell, of fires that rained from above and floods that swallowed the land. Fossil beds near the bays are littered with the bones of megafauna, mastodons, giant bison, and dire wolves, many showing signs of sudden, violent death. Could these depressions be mass graves, etched by a disaster so profound it reset entire ecosystems? What's chilling is how easily we've overlooked them. Today, many bays are just scenic ponds or fertile farmland, their apocalyptic origins buried under layers of peat and forgetfulness. But they're more than curiosities. If the impact theory holds, the Carolina Bays are a blueprint for chaos, proof that cosmic threats don't always leave a single crater. Sometimes they leave a scattering of wounds, each one a silent witness to a day the sky split open. And that's the lesson etched into these quiet basins. Disaster doesn't announce itself with a single bang. It can arrive in fragments, each piece rewriting the landscape in ways we're only beginning to decipher. The bays aren't just relics, they're reminders, because if the sky fell once, it could fall again, and next time we might not have 12,000 years to piece together what happened. There's a layer of soil so unassuming you could kick it aside with your boot, yet it holds the secret to one of Earth's most dramatic vanishings. Stretching from Arizona to the Carolinas, the black mat is a charcoal-colored ribbon no thicker than your finger, but its darkness speaks volumes. 12,800 years ago, something terrible happened. Below this mat lie the bones of mammoths, giant sloths, and saber-toothed cats, their fossils frozen in poses of sudden death. Above it, silence, a world stripped of giants, but the mat itself is the smoking gun packed with soot, nanodiamonds, and microscopic spikes of rare metals like iridium and platinum. These aren't the ingredients of a slow decline, they're the residue of apocalypse. Picture a day when the sky caught fire, a comet or asteroid fractured into pieces, screaming through the atmosphere and detonating in a series of airbursts, each explosion hotter than the surface of the sun. The blasts would have ignited wildfires from coast to coast, turning forests into ash and filling the sky with a pall of smoke thick enough to blot out the sun for years. The soot in the black mat is what rained down afterward, a global shroud of ruin, but the real clincher is the extraterrestrial debris, those nanodiamonds and rare metals. They're cosmic fingerprints, evidence of an impact so violent it vaporized rock and scattered it across the continent like gruesome confetti. What's chilling is how fast it all unfolded. One year, mammoths trampled through grasslands, the next gone. Pollen records show vegetation shifted overnight, as if someone flipped a switch. Warm adapted plants vanished, replaced by hardy shrubs and ferns, the botanical equivalent of a wasteland. Even human cultures weren't spared. The Clovis people, known for their distinctive spear points, disappeared from the archaeological record almost simultaneously. The black mat isn't just a grave for megafauna. It's a cultural reset button pressed by the cosmos. Yet the most haunting detail isn't the destruction, it's the precision. The mat isn't a messy splatter. It's a surgical strike, a layer so sharply defined it could have been laid down in a single season. That's the terrifying implication. Ecosystems that had thrived for millennia were undone in months. For comparison, imagine if every elephant, lion, and giraffe in Africa dropped dead next winter, leaving only rats and cockroaches to inherit the continent. That's the scale of loss we're talking about. Now, here's the twist. The black mat isn't just about the past. It's a mirror. Today, we're living through another abrupt shift human caused this time, where species are vanishing at rates unseen since the dinosaurs. The mat whispers a warning. Life is resilient, but not infinitely so. When the hammer falls, it falls fast, and the scars it leaves aren't just in the soil. They're in the empty spaces where giants once roamed, and in the stories we'll never get to hear. So the next time you walk through a field, look down. Beneath your feet might be another black mat in the making. The question isn't whether Earth will remember our era, it's what it will remember. There's a kind of fossil most people never hear about, not made of bone or leaf, but of pure electricity. When a bolt of lightning strikes sandy ground, the searing heat hotter than the surface of the sun instantly melts the silica, fusing it into twisted, glassy tubes called fulgurites. These eerie formations, named after the Latin word for lightning, fulgur, are nature's own sculptures, capturing the split-second fury of a storm in something solid enough to hold in your hand. But some fulgurites aren't just curiosities. They're time capsules, preserving clues to ancient climates so violent they turn the sky into a geologic chisel. Take the Libyan desert, where paleofulgurites lie half-buried in the sand, some dating back millions of years. These aren't the delicate, branching tubes you might find after a summer thunderstorm. They're thick, gnarled, and often clustered in dense fields, evidence of storms so frequent and intense they turned the landscape into a lightning rod. What could cause such electrical chaos? Climate scientists point to periods of extreme atmospheric instability, when temperature swings between land and air were amplified, turning entire regions into storm factories. Picture a Sahara not of endless dunes, but of roiling clouds and near-constant thunder, the air crackling with energy as bolt after bolt scarred the earth below. The scary part, we might be heading back in that direction. As global temperatures rise, studies suggest lightning frequency could increase by as much as 50% for every degree of warming. Warmer air holds more moisture, and more moisture means more convective energy, the fuel for thunderstorms. Already, places like Venezuela's Catatumbo Delta experience hundreds of lightning strikes per hour during peak seasons. If fulgurites are fossils of past electrical mayhem, future geologists might find ours in layers as thick as those in Libya. But fulgurites aren't just weather vanes. They're forensic tools. By analyzing their chemical composition, researchers can trace ancient atmospheric conditions. Some contain trapped gases or isotopes that reveal humidity levels, even wind patterns from millennia ago. Others, found in now arid regions, hint at lost wetlands or shifting monsoons. These glassy time machines tell us that climate doesn't just change, it flickers, with periods of calm punctuated by violent swings. Then there's the sheer power they represent. A single lightning bolt carries enough energy to power a home for weeks. Multiply that by the millions of strikes that formed fossil fulgurite fields, and you're looking at a force capable of reshaping landscapes. In some places, fulgurites are so abundant they've been mined for industrial abrasives or even jewelry, a strange afterlife for what was once raw atmospheric rage. What's haunting is how fragile these records are. Unlike stone or bone, fulgurites are brittle, easily crushed by a careless step. Yet against all odds, some have survived eons, waiting for us to decode their messages. They remind us that the sky doesn't just rain water or snow. It etches its history into the ground, one electrified scar at a time. And if we're paying attention, these glassy threads might just help us predict when the next storm epoch begins. Because here's the truth, lightning isn't just weather. It's a sculptor, a chemist, even a chronicler. And as the planet warms, its pen might be poised to write a new chapter, one we'll read in the fulgurites left behind. Beneath the churning waves of the Atlantic Ocean lies one of Earth's most astonishing diaries, a sprawling, underwater mountain range etched with stripes like a cosmic barcode. The Mid-Atlantic Ridge, a colossal seam that snakes down the center of the ocean, is more than just a geological curiosity. Its alternating bands of light and dark rock are a cryptic record of Earth's magnetic personality, a story of flips, collapses, and rebirths written in stone. These stripes aren't random. They're the fingerprints of a planet that can't decide which way is north. Here's how it works. As molten rock erupts from the seafloor and cools, tiny magnetic minerals inside it lock into place, aligning with Earth's magnetic field like microscopic compass needles. Over millennia, as the seafloor spreads outward from the ridge, it preserves these snapshots of the planet's magnetic orientation. Normally, you'd expect a uniform pattern. But the Mid-Atlantic Ridge's stripes tell a wilder tale, one where the magnetic field has reversed hundreds of times, turning compasses upside down and leaving behind a zebra-striped testament to chaos. The scary part, these reversals aren't just ancient history. Right now, Earth's magnetic field is weakening at an alarming rate with the South Atlantic anomaly, a vast region where the field is unusually thin, growing larger every year. Satellites passing through it glitch or shut down, as if the planet's electromagnetic immune system is faltering. If the trend continues, we could be on the brink of another flip. And while that might sound like a slow, harmless process, the geologic record suggests otherwise. Dig into extinction events, and you'll find eerie overlaps with past reversals. The Lashump excursion, a brief flip 41,000 years ago, coincided with the demise of Neanderthals and a surge in cosmic radiation detected in ice cores. Even more chilling, the fossil record shows spikes in mutations during these periods, species suddenly sporting odd deformities, as if bombarded by invisible forces. The reason, without a strong magnetic field, Earth's shield against solar and cosmic radiation weakens, leaving life exposed to the full fury of space. But here's the twist, not all reversals spell doom. Some pass with barely a whisper in the fossil record. The difference might lie in timing. A slow, staggered flip could give life room to adapt, while an abrupt collapse could trigger catastrophe. And that's the puzzle scientists are racing to solve. By studying the Mid-Atlantic Ridge's stripes, they're piecing together clues about how past reversals unfolded, how long they took, how weak the field became, and what the fallout was for life on Earth. The real lesson of these magnetic stripes isn't just about compasses going haywire. It's about vulnerability. Modern civilization depends on that invisible shield more than we realize. GPS, power grids, even migratory animals all rely on a stable magnetic field. A full reversal could disrupt everything from satellite communications to whale navigation. Yet the rocks also offer a glimmer of hope. However chaotic these flips seem, Earth's field has always recovered, rebuilding itself like a phoenix from the ashes. So the next time you glance at a compass, remember, its steady needle is the exception, not the rule. The Mid-Atlantic Ridge's stripes are proof that our planet's magnetic heart is restless, and its next beat could rewrite the future. There's something unsettling about the way so many dinosaur fossils seem frozen in the same agonized pose, necks wrenched backward, jaws gaping, limbs contorted as if caught mid-spasm. This eerie stance, nicknamed the dinosaur death pose, isn't just a quirk of fossilization. It's a silent scream from the past, a clue to the final moments of creatures that ruled the Earth. From the badlands of Montana to the deserts of Mongolia, skeletons preserved this way tell a chilling story. These animals didn't just die, they suffocated. The science behind this posture points to something far darker than old age or injury. When vertebrates die from oxygen deprivation, whether drowning, poisoning, or respiratory failure, their muscles often contract violently, pulling the head backward in what's called an opisthetonic spasm. In modern birds, alligators, even horses, this same pose appears in cases of asphyxiation. But for dinosaurs to die this way en masse across continents and species suggests a catastrophe so vast it choked the very air they breathe. Now rewind to the end of the Cretaceous. The asteroid impact at Chicxulub was just the opening act. As wildfires raged and dust blotted out the sun, another killer crept into the atmosphere: volcanic gases from the Deccan Traps eruptions. Hydrogen sulfide, carbon dioxide, and sulfur dioxide would have poisoned the air in lethal concentrations, searing lungs and starving tissues of oxygen. Imagine herds of triceratops collapsing mid-stride, their muscles locking into that grotesque arch as their bodies fought for one last breath. Even marine reptiles like mosasaurs, washing ashore with spines bent backward, fell victim, proof the toxins permeated land and sea. But here's what's haunting: those same gases are lurking in Earth's arsenal today. Volcanic, flood basalt events like the Deccan Traps are rare, but smaller eruptions like Indonesia's Mount Tambora in 1815 can still alter global climates. When Tambora blew, it unleashed a sulfurous veil that triggered the year without a summer, killing crops as far away as New England. Now scale that up. Climate models suggest a modern super-eruption could plunge us into a volcanic winter with acid rain and toxic haze lasting years. The dinosaur death pose isn't just a relic. It's a rehearsal, yet there's a twist in this fossilized tragedy. Not all dinosaurs died this way. Some skeletons lie peacefully, suggesting quicker, less painful ends, perhaps from the asteroid's immediate blast or tsunamis. The difference between a contorted corpse and a serene one might come down to where they were when the skies turned foul. Low-lying areas would have trapped heavier than air poisons like hydrogen sulfide, creating deadly invisible lakes of gas. Higher ground, meanwhile, might have offered fleeting refuge. That's the real warning etched into these bones. Extinction isn't uniform. It's a patchwork of microclimates and luck, where altitude, geography, and even body size decide who gasps and who gets off easy. As we pump our own atmosphere full of pollutants, from industrial smog to methane leaks, the dinosaur death pose whispers a question. When the next great choke comes, will we be on the high ground or in the gas? Namibia's sun-baked deserts seem like the last place you'd expect to find clues about a frozen planet. Yet scattered across this arid landscape are boulders etched with deep, parallel grooves, the unmistakable scars of glaciers. These rocks shouldn't be here. Glaciers need cold, and Namibia sits squarely in the tropics. But 700 million years ago, this land wasn't just chilly. It was buried under miles of ice, part of a planetary deep freeze so extreme scientists call it Snowball Earth. Imagine a world where ice stretched from pole to pole, encasing oceans in a kilometer-thick shell and turning continents into barren wastelands. Temperatures plummeted to -50 degrees Celsius, colder than modern Antarctica. Even at the equator, the only liquid water might have been hidden beneath the ice, in pitch-black pockets kept barely above freezing by geothermal heat. This wasn't just an ice age, it was Earth as a cosmic snowball, a glittering tomb spinning through space. Yet life didn't just endure, it thrived. How? The answer lies in those scratched boulders. When geologists examined them, they found something astonishing. layers of iron-rich sediment sandwiched between glacial deposits. These rusty stripes tell of a brief but dramatic thaw, a moment when the ice cracked open, allowing oxygen to react with dissolved iron in the seawater. This great rust event suggests Snowball Earth wasn't a single, unbroken freeze. It pulsed with ice sheets advancing and retreating like a slow planetary heartbeat. And in those fleeting thaws, life found refuge. Microbes clinging to hydrothermal vents or surviving in slushy brine channels would have seized every opportunity to rebound. Some scientists think these extreme swings actually drove evolution, forcing organisms to adapt or die. The descendants of those survivors, including the ancestors of all complex life today, carry genetic blueprints for resilience written during this icy trial by fire. But here's the twist: Snowball Earth might be more than just a cautionary tale. It could be a roadmap. Astronomers searching for life on icy moons like Europa or Enceladus study these ancient glacial deposits for clues. If life persisted under Earth's crushing ice sheets, could it exist in the subsurface oceans of distant worlds? The same geothermal vents that sheltered microbes here might be nurturing alien organisms right now, in the dark beneath frozen crusts. Then there's the climate parallel. Snowball Earth didn't happen by accident. It was likely triggered by a drop in greenhouse gases, perhaps as weathering rocks sucked carbon dioxide from the atmosphere. Today, we're racing in the opposite direction, pumping CO2 into the sky at unprecedented rates. But the lesson isn't just about imbalance, it's about rebound. When Snowball Earth finally ended, volcanic eruptions rebuilt the atmosphere, thawing the planet so fast it might have triggered an explosion of new life. The scars in Namibia's rocks don't just warn of catastrophe, they whisper hope, because buried in those glacial scratches is a paradox. Sometimes the harshest winters prepare the ground for the richest springs. And if life could emerge stronger from a planet-sized icebox, maybe, just maybe, there's a path through our own climate crisis. The key is reading the rocks before it's too late. Beneath the sparkling blue waters of the Mediterranean lies a secret so vast it defies belief. A layer of salt 2 miles thick, buried under centuries of sediment. This isn't just ordinary sea salt. It's the ghost of an ocean that vanished almost overnight, leaving behind a silent graveyard of crystallized brine. 5.6 million years ago, the Mediterranean wasn't the bustling marine highway we know today. It was a scorching wasteland, a hollowed-out basin where water once flowed, but now only dust devils danced. Scientists call this apocalyptic event the Messinian salinity crisis, a time when the Mediterranean dried up and turned into the world's largest salt flat. How does an entire sea disappear? The answer lies in Gibraltar. Back then, the narrow strait separating Europe from Africa wasn't just a passage. It was a bottleneck, a fragile dam of rock and sediment that kept the Atlantic at bay. But as tectonic shifts and falling sea levels weakened this natural barrier, the Mediterranean's lifeline was cut off. With no inflow from the ocean and evaporation outpacing river inputs, the basin began to wither. Shorelines retreated by hundreds of miles, leaving behind vast salt pans where ships now sail. The deeper it drained, the saltier the remaining water became, until even hardy marine life suffocated in the toxic brine. Then came the final act. As the basin's last pools evaporated, minerals like gypsum and halite common table salt crystallized into layers thicker than some mountains. These deposits aren't just remnants, they're a countdown marking each phase of the sea's death throes. But the most haunting evidence isn't in the salt itself. It's in the canyons. Rivers like the Nile and the Rhone, suddenly deprived of their endpoint, carved gorges thousands of feet deep into the exposed seabed, trenches so vast they dwarf the Grand Canyon. These fossilized riverbeds, now buried under modern sediments, are the scars of a world adjusting to the unthinkable, an ocean gone missing, and then catastrophe in reverse. When the Atlantic finally breached Gibraltar again, it didn't trickle back in. It exploded through the strait with the force of 1,000 Niagaras, filling the basin in what geologists estimate could have been as little as 2 years. The Gibraltar Canyon, a submerged gorge deeper than the Grand Canyon, was carved in this deluge, a permanent reminder of the ocean's violent return. Imagine witnessing that, a wall of water hundreds of feet high, roaring across a desert basin at speeds faster than a bullet train, swallowing entire landscapes in days. What's chilling is how quietly this apocalypse unfolded in the geologic record. Unlike asteroid strikes or volcanic winters, the Mediterranean's disappearance left no global extinction layer. Life simply adapted, migrated, or died unnoticed, but the salt tells another story, one of fragility. Our planet's balance is more delicate than we think. Today, the Mediterranean relies on Gibraltar's narrow gateway to stay full. If sea levels dropped just a few hundred feet, history could repeat itself. The real lesson of the lost Mediterranean isn't just about the past, it's about change. Oceans aren't permanent, coasts aren't fixed, and the forces that shape our world don't always move at human speed. Sometimes they rewrite the map in a geological blink. So the next time you dip your toes in the Mediterranean, remember, you're standing on the ghost of a vanished sea, and the salt beneath your feet is its last whisper. On the morning of June 30th, 1908, a fireball brighter than the sun tore across the Siberian sky before detonating with the force of a 12-megaton bomb, 800 times more powerful than Hiroshima. The blast flattened 80 million trees across 800 square miles of remote taiga, snapping trunks like matchsticks in a perfect radial pattern radiating outward from ground zero. Yet when scientists reached the remote Tunguska site decades later, they found something baffling: no crater, no smoking gun, just a silent forest of toppled giants, their roots all pointing eerily away from an invisible epicenter. This bizarre destruction pattern holds the key to one of geology's most unsettling realizations. Tunguska wasn't unique. Scattered across ancient peat bogs from the Carolinas to Kazakhstan are eerily similar treefall graveyards, their trunks aligned in those same telltale radial swaths. The difference: these date back thousands of years, some even predating human civilization. Each one tells the same story. An object, likely a stony meteor or comet fragment, exploding high in the atmosphere with enough force to level forests but leave the ground beneath untouched. These aren't impacts, they're airbursts, cosmic bombs detonating in midair like the Chelyabinsk meteor of 2013, but with exponentially more destructive power. What's chilling is how often these events might recur. Modern modeling suggests Tunguska-scale airbursts could happen every few hundred years, with smaller ones every few decades. The scars they leave are subtle, no gaping craters, just twisted trees and occasionally strange chemical traces in the soil. At Slovakia's Kofel site, geologists found a layer of jumbled rock fragments and melted glass dating back 9,000 years. Evidence of an airburst so hot it fused stone into a natural version of trinitite, the glassy residue left by atomic tests. Similar deposits appear in the Greenland ice cores, synchronized with spikes in ammonium and nitrate hallmarks of widespread wildfires ignited by superheated shockwaves. Yet the real warning lies in our blind spots. Unlike large asteroids, which telescopes can track years in advance, Tunguska-sized objects between 60 and 200 meters often slip through detection networks until it's too late. The Chelyabinsk meteor, just 20 meters wide, arrived completely unannounced in 2013, injuring over 1,500 people with its shockwave. Ancient airburst sites suggest far larger near misses. The Mahuika crater off New Zealand's coast may mark a 500-meter comet fragment that detonated over the Pacific around 1540, triggering tsunamis recorded in Aboriginal oral histories. Now layer on another threat, climate feedback. When an airburst ignites wildfires across millions of acres, as Tunguska did, the smoke and soot could linger for years, amplifying cooling effects. Ice cores from 1790 show a mysterious sulfate spike coinciding with Aboriginal accounts of a sky fall in Australia, hinting at a potential airburst-triggered climate anomaly. In a world already grappling with global warming, adding an atmospheric smoke blanket could push ecosystems past tipping points. But here's the twist: these airbursts might also explain some of history's greatest enigmas. The sudden collapse of advanced societies like the Akkadian Empire or the Indus Valley civilization aligns suspiciously with charcoal-rich soil layers and abrupt climate shifts in their regions. Could fragmented comets have played a role? Unlike volcanic eruptions or earthquakes, airbursts leave few obvious ruins, just toppled trees, scorched earth, and confused survivors left to interpret the celestial wrath. That's why Tunguska matters. It's not just a historical curiosity. It's a test case, a blueprint for disasters we're only beginning to recognize in the geologic record. And as we scan the skies for planet killers, the real danger might not be the boulders we concede, but the ones that explode before they even hit the ground. The trees remember. The question is, will we? In the quiet prairie lands of Washington state, the Earth has been keeping a cryptic secret: thousands of dome-shaped soil mounds, some as tall as a person and as wide as a truck, dotting the landscape like a giant's fingerprints. These are the Mima Mounds, and for over a century their origin baffled scientists. Early settlers spun myths about gophers building them over generations, while others guessed they were Native American burial sites. But the truth is far more unsettling. These unassuming humps of dirt might be the aftermath of apocalyptic earthquakes, trembling reminders that the Pacific Northwest is sitting on a geologic time bomb. Dig into one of these mounds and you won't find bones or animal dens. Instead, you'll hit a layer of jagged rocks and coarse gravel, all sitting atop a base of fine, compacted silt. This isn't the work of creatures, it's the signature of liquefaction, a phenomenon where solid ground turns to quicks, and during violent shaking, when a megaquake rips through a subduction zone like the Cascadia Fault, the force can send shockwaves through waterlogged soils, churning layers like a blender and forcing heavier stones upward into these eerie, uniform piles. The Mima Mounds aren't just odd geology. They're the fossilized aftershocks of disasters we've yet to witness firsthand. What's terrifying is the scale of the quakes required to sculpt them. Modern liquefaction, like what hit Japan during the 2011 Tohoku earthquake, leaves behind scattered sand volcanoes and fissures, nothing as organized or enduring as the Mimas. For the ground to heave into thousands of near-identical mounds, the shaking would need to be sustained, like a prolonged drumroll of seismic violence. That's exactly what happens during a full margin rupture of the Cascadia subduction zone, where the Juan de Fuca plate grinds beneath North America. Historical evidence suggests these quakes hit every 300 to 500 years, with the last one striking in 1700. We're overdue, but here's the twist. The Mima Mounds might also hold clues to survival. Their distribution isn't random. They cluster in zones where the soil composition is just right, loose enough to liquefy but cohesive enough to hold shape after the shaking stops. By mapping them, geologists are essentially mapping prehistoric earthquake intensity, identifying which areas turn to slurry when the big one hit. For modern cities like Seattle or Portland, that's a blueprint for danger. Neighborhoods built on similar soils today could face not just collapsing buildings, but streets swallowing themselves as the Earth loses its grip. Yet the mounds aren't just doomsayers. They're teachers. In Chile, where subduction quakes are frequent, engineers have studied liquefaction patterns to design foundations that float on unstable ground, using shock-absorbing materials to mimic the way Mima Mounds redistribute stress. Even nature seems to adapt. Prairie plants on the mounds have deeper roots, anchoring themselves against future upheavals. There's a strange resilience in these lumpy fields, a reminder that the Earth doesn't just destroy. It rebuilds, so the next time you drive past an unassuming grassy hummock, remember, it might be more than a bump in the road. It could be a message from the past, written in soil and stone, warning us that the ground beneath our feet isn't as solid as it seems. And in the Pacific Northwest, that message is growing louder with every silent year that passes. Beneath the quiet bayous and oil fields of Louisiana lies a hidden monument to violence, a series of colossal sand waves, each 150 feet tall, frozen in time like the echoes of a forgotten tsunami. These aren't ordinary dunes, they're mega-ripples carved by a wall of water so powerful it defies imagination, and their origin story is written in the same cosmic ink as the dinosaurs' demise. 66 million years ago, when the Chicxulub asteroid slammed into the Yucatan Peninsula, it didn't just unleash fire and darkness. It kicked the ocean like a pebble in a pond, sending tsunamis racing across the Gulf of Mexico at speeds rivaling jet planes. The scale of these waves is almost incomprehensible. Computer models suggest the initial surge could have been a mile high near the impact site, taller than any modern skyscraper. By the time it reached what's now Louisiana, it had slowed, but still towered hundreds of feet, crashing inland for miles, dragging entire forests, boulders, and even chunks of the continental shelf with it. The mega-ripples are what remained when the water retreated, the sand beneath the seafloor sculpted into these eerie, undulating patterns. Unlike ordinary waves which leave fleeting marks, these ripples were buried under layers of sediment, preserved like a fossilized scream. What's chilling is how fresh they look. Normally, geologic forces smooth out such features over millennia, but these mega-ripples are pristine, their sharp crests and troughs perfectly intact. That's because they were sealed away almost immediately, protected by a blanket of debris that settled as the ocean calmed. For paleontologists, it's like stumbling onto a crime scene where the evidence hasn't aged a day. The ripples even hold trapped microfossils, tiny marine organisms that were alive one moment and buried the next, their shells now timestamps pinpointing the exact day of the disaster. But here's the unsettling part. Chicxulub's tsunami wasn't a one-off. Earth's history is littered with similar events. 8,000 years ago, a landslide off Norway triggered a wave that drowned coastlines from Scotland to Greenland. And in Alaska, geologists have found mega-ripples from tsunamis unleashed by collapsing glaciers. The difference, those were local disasters. Chicxulub was global. Its waves didn't just hit the Gulf, they circled the planet, bouncing off continents like echoes in a cavern. Sediment cores from New Zealand show layers of disturbed rock matching the impact's timing, proof that nowhere was safe. Now imagine a similar strike today. Modern early warning systems might buy coastal cities minutes, not hours, to evacuate. And while we're better at tracking asteroids than dinosaurs were, we're still vulnerable. In 2013, a meteor just 65 feet wide exploded over Chelyabinsk, Russia, with the force of 30 Hiroshima bombs. A Chicxulub-scale impact would be millions of times stronger. The mega-ripples in Louisiana are more than geologic curiosities, they're a stress test for civilization. Yet buried in that sand is also a strange kind of hope. Life rebounded after Chicxulub, diversifying into the world we know today. The mega-eruptions remind us that catastrophe isn't the end, it's a reset. The question is, will we be ready when the next wave comes? Because the Earth keeps score, and sometimes its ledger is written in sand. 2 miles beneath the churning waves of the Arctic Ocean, along Norway's volcanic mid-Atlantic ridge, lies a place where geology defies the imagination, a sprawling network of towering mineral chimneys belching superheated, metal-laden fluids into the frigid darkness. Scientists call this alien landscape Loki's Castle, named after the Norse trickster god, and for good reason. These hydrothermal vents don't just challenge our understanding of life's limits, they rewrite the rules entirely. The scalding plumes, rich in sulfur and iron, sustain thriving ecosystems of extremophiles microbes that thrive in conditions that would liquefy most organisms. But here's the astonishing part. These deep-sea oases might be more than just biological curiosities. They could be time machines offering a glimpse into how life clawed its way back after Earth's most devastating catastrophes. Picture this: 4 billion years ago, our planet was a molten hellscape bombarded by asteroids and volcanic fury. The surface was uninhabitable, but below the waves, hydrothermal vents like Loki's Castle may have served as life's first incubators. The chemistry is uncanny. The vent fluids, heated by magma and loaded with hydrogen sulfide, mimic the primordial soup theorized to have spawned Earth's earliest organisms. Even more compelling, these microbes don't just survive without sunlight, they flourish, using chemosynthesis to convert toxic minerals into energy. It's a survival playbook written in the planet's infancy, one that could have allowed life to endure even when the surface was sterilized by asteroid impacts or choked by volcanic winters. Now, fast forward to modern threats. If another global catastrophe, whether nuclear winter, supervolcanic eruption, or asteroid impact, wiped out surface life, extremophiles in places like Loki's Castle might be the last survivors. Their genetic blueprints could literally reboot ecosystems, just as they might have done eons ago. Researchers have already discovered microbes here with staggeringly resilient traits, from DNA repair mechanisms that shrug off radiation to enzymes that function in near-boiling temperatures. Some even form symbiotic relationships with larger organisms, like the ghostly Rimicaris shrimp that farm bacteria on their own bodies, a snapshot of how complex life might re-emerge from microbial alliances after a reset. But the real revelation lies in the vent's mineral deposits. Loki's Castle isn't just spewing fluids, it's constructing new land. The metals precipitating from the plumes form intricate chimneys, some growing several feet per year. These structures aren't static. They collapse, reform, and evolve, creating a dynamic mosaic of microhabitats. In a post-apocalyptic scenario, such processes could seed new niches for life to exploit, accelerating recovery. It's a tantalizing parallel to the fossil record, where hydrothermal deposits often coincide with periods of mass extinction and subsequent diversification. What's haunting is how fragile these systems are. Deep sea mining operations already vent sites for their rich metal deposits, risking irreversible damage to these biological arcs. Yet their value isn't just in what they can mine, it's in what they can teach. By studying Loki's Castle, we're not just probing the origins of life, we're stress-testing its resilience, uncovering strategies that could one day save our own species. Because if the vents hold the secret to surviving Earth's worst disasters, they might also hold the key to thriving on worlds beyond ours, where icy moons like Europa or Enceladus hide similar hydrothermal depths beneath their frozen shells. So the next time you hear about extremophiles, remember, they're not just oddities, they're the ultimate survivors, the keepers of a billion-year-old playbook for enduring the unthinkable. And in the swirling, metallic plumes of Loki's castle, Earth whispers its oldest lesson. Life doesn't just persist, it adapts, it conquers, and sometimes it rises from the ashes or the abyss stronger than before. Deep in the frozen heart of Siberia, a layer of rock tells a story of poison, not from a venomous creature, but from the planet itself. The Siberian Traps, a vast expanse of ancient lava flows that once covered an area larger than Europe, didn't just bury the landscape under miles of molten rock. They pumped something far deadlier into the environment: nickel. Not the nickel we use in coins or batteries, but a toxic deluge that seeped into the oceans, suffocating life on a scale almost too horrifying to comprehend. 252 million years ago, during the Great Dying, Earth's deadliest mass extinction, these volcanic eruptions didn't just darken the skies, they turned the seas into a chemical wasteland. Here's how it happened. As the Siberian Traps erupted, the lava didn't just stay on the surface. It intruded into coal and salt deposits, superheating them until they released clouds of chlorine, carbon dioxide, and critically, nickel particles. This wasn't a slow leak. It was a geochemical explosion, with nickel concentrations in some marine sediments spiking to levels 50 times higher than normal. For ocean life, it was a death sentence. Nickel, even in trace amounts, disrupts enzymes essential for respiration and photosynthesis. Algae died first, collapsing the base of the food web. Then, as oxygen levels plummeted, larger creatures succumbed to suffocation and starvation. The fossil record from this period is a horror show. Reefs turned to graveyards, seabeds littered with the twisted shells of organisms that literally choked on the water itself. But here's what's chilling: we're doing it again. Modern nickel mining, driven by demand for batteries and electronics, releases thousands of tons of this same metal into rivers and oceans every year. In places like Norilsk, Russia, a city built atop the very same Siberian Traps, mining operations have turned rivers blood red with nickel runoff. The parallels are unnerving. While our pollution hasn't reached Permian levels, the mechanism is identical: extracting nickel from the earth and unleashing it into ecosystems unequipped to handle the onslaught. The difference: the Siberian Traps took hundreds of thousands of years to devastate the planet. We're achieving similar contamination in mere decades. Yet there's a twist in this toxic tale. Nickel isn't inherently evil. In fact, it's essential, a micronutrient many organisms need in tiny doses. The problem isn't the element itself, but the scale and speed of its release. Nature operates on balance, and when that balance is shattered, disaster follows. The Siberian Traps didn't just poison the oceans, they rewired Earth's chemistry, pushing systems past tipping points we're only now beginning to understand. Today, as we dredge up nickel for clean energy technologies, we're walking the same tightrope. The same metal that could power a greener future might also carry echoes of the planet's deadliest chapter. So what's the lesson hidden in these ancient rocks? It's not that nickel is the enemy. It's that Earth systems are finely tuned, and when we yank one thread too hard, the whole tapestry can unravel. The Siberian Traps are a warning written in stone: poison the well, and eventually, even the survivors will thirst. The question is, will we read the message in time, or become the next layer in the geologic record? Along the misty shores of Washington and Oregon, a line of skeletal cedar stumps rises from the tidal flats like gravestones in a drowned cemetery. These are the ghost forests of Cascadia, silent witnesses to a violence so profound it dragged entire coastlines underwater in minutes. Unlike ordinary dead trees, these stumps didn't rot or fall. They were preserved in a state of eerie perfection, their bark still intact, their roots still anchored in soil that hasn't seen daylight for centuries. The secret to their preservation: salt water. When the last great Cascadia earthquake struck in 1700, the land abruptly dropped 6 feet or more, plunging living forests into the intertidal zone. Seawater rushed in, pickling the trees in brine and stopping decay in its tracks. Now, these spectral sentinels are more than just relics. They're a countdown clock ticking toward the next catastrophe. Dig into the sediment around these stumps, and the story gets even darker. Beneath the peat and sand lies a layer of tsunami sand, coarse grains hurled inland by the colossal waves that followed the quake. Native oral histories describe the event in chilling detail: whole villages vanishing overnight, canoes flung into treetops, and thunder from the ocean that shook the world. Modern science confirms their accounts. Core samples show at least 41 of these megaquakes over the last 10,000 years, averaging one every 243 years. The last was 324 years ago. By the ghost's math, we're overdue. But here's what's haunting: the trees aren't just timestamps, they're stress tests. By studying their rings, scientists can pinpoint the exact year, sometimes even the season they died. Many show growth suppression in the decades before the quake, a sign of increasing tectonic strain that warped the land subtly, starving roots of nutrients. Others have reaction wood, twisted grain patterns from leaning precariously as the ground deformed. These aren't just dead trees, they're diaries, recording every shudder and sigh of a fault line waking from its slumber. The real warning, though, lies in their distribution. Ghost forests aren't random. They cluster in subsidence zones, areas most prone to sinking during a quake. Modern LiDAR scans reveal these zones with terrifying clarity, low-lying regions that could become instant lagoons when the next rupture hits. Cities like Seattle and Portland are built on sturdier uplands, but critical infrastructure, ports, highways, pipelines, often traces these ancient death traps. The ghosts are literally mapping our vulnerabilities. Yet there's a twist in this arboreal oracle. Some stumps aren't alone. Saplings of the same species now grow beside them, their roots threading through the bones of their ancestors. It's a paradox. The very forces that drowned these forests also created new wetlands, fertile grounds for the next generation. The lesson isn't just about destruction, it's about renewal. Cascadia's ghosts don't just whisper of doom. They hum a refrain as old as the planet itself: collapse and rebirth, catastrophe and resilience. The question isn't whether the land will drop again. It's when, and as the tides creep higher around these wooden prophets, their message grows harder to ignore. They've seen the future, and it's written in salt water and sand. China's lowest plateau holds one of Earth's most meticulous climate diaries, a sprawling archive of dust stacked in layers thicker than skyscrapers. Unlike ordinary soil, this golden silt didn't form from rotting plants or crumbling bedrock. It fell from the sky, carried by winds so fierce they scoured entire continents and dumped their cargo in towering drifts. Over millions of years, these deposits grew into a geologic library, each band of loess encoding details about ancient storms, droughts, and even the direction of long-vanished winds. But the real revelation lies in the rhythm of these layers. They pulse in sync with ice ages, thickening during glacial periods when deserts expanded and shrinking when warmer rains returned. Now, as modern deserts creep outward and droughts intensify, the plateau's silent strata raise an unsettling question. Are we scripting the next chapter in this dusty saga? Unraveling these layers is like reading tree rings on a planetary scale. During ice ages, colder oceans meant weaker monsoons, leaving Central Asia's landscapes parched and vulnerable. Winds ripped fine particles from exposed riverbeds and dry lake basins, carrying them southeast to the plateau. The result: loess accumulated at staggering rates, sometimes a foot every century. But between glaciations, the story flipped. Stronger rains stabilized the soil, and lowest deposition slowed to a trickle. These alternating bands aren't just dirt. They're a barometer of global aridity, a record of how Earth's climate tilts between wet and dry, fertile and barren. What's startling is how precise these archives are. Within the loess, scientists find microscopic fossils of land snails, their shells preserving isotopic signatures of past humidity. Pollen grains reveal shifts in vegetation, from grasslands to forests and back again. Even the dust itself holds clues. Its grain size hints at wind strength, while its mineralogy traces the dust's origin to specific river valleys now buried under dunes. Together, these details reconstruct Ice Age climates with resolution unmatched by ice cores or ocean sediments. The plateau doesn't just record change. It films it frame by dusty frame, yet the most urgent message isn't about the past, it's about the present. Today, the lowest plateau is eroding back into dust, its fragile soil stripped by overgrazing and deforestation. Similar patterns are emerging worldwide, from the American Great Plains to the Sahel. Modern dust storms, like the ones turning Beijing's skies orange or choking Phoenix in Haboobs, carry eerie echoes of the plateau's formation. Satellite data shows global dust emissions have increased by 25% since the 1970s, much of it from areas where agriculture and drought collide. We're not just observing history, we're repeating it. The difference this time: speed. Natural dust cycles unfolded over millennia, giving ecosystems time to adapt. Human-driven desertification works in decades, and the consequences ripple far beyond barren fields. Dust from the Gobi Desert fertilizes plankton blooms in the Pacific, altering marine food webs. Saharan dust crossing the Atlantic can suppress hurricanes but also carries pathogens harmful to coral reefs. Even the Arctic isn't immune. Dark dust settling on ice accelerates melting by absorbing sunlight. The lowest plateau's layers warn us, dust isn't just a local nuisance. It's a global lever capable of tipping climates and ecosystems alike. But there's hope in this gritty archive too. Chinese conservationists have transformed parts of the plateau by terracing slopes and planting deep-rooted grasses, cutting erosion by over 50%. These efforts mimic nature's own stabilization during warm periods, proving that even the most degraded landscapes can heal. The lowest teaches us that deserts aren't permanent, they're phases shaped by climate and stewardship. So the next time you see dust dancing on the wind, remember, those tiny particles once built mountains, and the choices we make today, how we farm, how we conserve, will determine whether the next layers tell a story of resilience or ruin. The plateau's message is clear. The sky isn't just above us, it's beneath our feet, waiting to rise again. 2 billion years ago, an asteroid larger than Table Mountain slammed into what is now South Africa with such force it vaporized rock, melted continents, and left a scar wider than the Grand Canyon, the Vredefort impact structure. Today, this ancient apocalypse is more than just a geologic curiosity. It's the reason Johannesburg exists. Hidden in the shattered rocks of this crater lies one of Earth's richest gold deposits, a treasure trove forged not by slow tectonic processes, but by the instant hell of a cosmic collision. The very violence that nearly sterilized the planet also concentrated its riches, weaving destruction and fortune into a single, paradoxical thread. How does an asteroid create gold? The answer lies in the physics of extreme pressure. When the Vredefort impactor struck, it didn't just leave a hole, it unleashed shockwaves hotter than the sun's surface, ripping through the crust and redistributing metals like a cosmic blender. Pre-existing gold veins, once scattered thinly in the rock, were liquefied and injected into fractures formed by the impact, creating dense, minimal loads. The same forces that obliterated landscapes also acted as nature's own alchemist, transforming diffuse particles into concentrated wealth. Even the crater's unique geology, a multi-ringed bullseye of uplifted and melted rock, created perfect traps for gold-bearing fluids to accumulate. Without this cataclysm, South Africa's gold might have remained locked in inaccessible traces, never sparking a rush that shaped empires, but the gold came at a price. The mines of Johannesburg, which owe their existence to Vredefort, are among the deepest and deadliest on Earth. Workers descend into shafts that plunge over 2 miles underground, where rock temperatures exceed 140 degrees Fahrenheit and seismic tremors rattle the tunnels like ghostly aftershocks of the original impact. The human toll is staggering. Thousands of miners have died in collapses, fires, and equipment failures over the past century, while countless more suffer from silicosis after inhaling gold-laden dust. The crater's legacy isn't just glittering nuggets, it's a cycle of exploitation and sacrifice as old as the mines themselves. The environmental cost is equally stark. Acid mine drainage from abandoned shafts has poisoned rivers, turning water sources toxic with heavy metals. The Witwatersrand Basin, the gold-rich zone within the crater, is now pockmarked with slimes, dams, mountains of radioactive waste left after uranium-laden ore was processed. These residues leak carcinogens into the soil, a slow-motion echo of the asteroid's devastation. In a cruel twist, the same event that gifted humanity with wealth also burdened it with a toxic inheritance. Yet Vredefort's story isn't unique. From Sudbury's nickel deposits in Canada to the platinum-laced rocks of Siberia's Norilsk region, Earth's richest metal reserves often trace back to impacts. These catastrophes didn't just bring destruction, they reset the planet's chemistry, shuffling elements into configurations that wouldn't exist under gentler conditions. The gold rush was inevitable. The real question is whether we'll learn from it. Because the next time a cosmic windfall strikes, whether in the form of asteroids or the green energy metals we now scour the Earth for, will we repeat the same cycle of boom and ruin? The Vredefort crater doesn't just hold gold, it holds a mirror. In its shattered rocks we see our own reflection, a species drawn to glittering rewards yet struggling to bear their weight. The asteroid's gift was a paradox, a fortune forged in fire, and a warning written in stone. Beneath the peat bogs and rolling hills of eastern Scotland lies a layer of sand that doesn't belong, a gritty, foreign stripe sandwiched between ancient soil and clay. To the untrained eye, it's just sediment, but to geologists, it's the smoking gun of a nightmare, the Storiga Slide. A cataclysmic underwater landslide that unleashed a tsunami taller than the Statue of Liberty 8,000 years ago. The wave didn't just crash onto shores, it invaded, surging miles inland, drowning coastlines from Norway to Greenland, and leaving behind these eerie sand deposits as its only calling card. What's terrifying isn't just the scale of the disaster, it's the trigger. The slide was set off by something deceptively simple, the destabilization of methane-rich seafloor sediments after the last ice age's glaciers melted. And with today's warming oceans, the same forces are stirring again. The mechanics of the Storiga Slide read like a disaster movie script. Off Norway's coast, a slab of seafloor the size of Kentucky, over 2,000 cubic miles of sediment suddenly broke free, collapsing down the continental slope at speeds approaching 100 miles per hour. The energy released was equivalent to thousands of nuclear bombs, displacing enough water to send a 300-foot wave racing across the North Atlantic. Coastal settlements vanished overnight. In the Shetland Islands, sand layers found 25 miles inland and 130 feet above sea level mark the tsunami's reach. But the real smoking gun lies in the sand's composition. Unlike normal beach sand, these grains are angular and mixed with deep-sea microfossils, proof they were ripped from the ocean floor and hurled onto land by sheer hydraulic force. What's chilling is how ordinary the cause was. The slide wasn't triggered by an earthquake or asteroid. It was set off by the slow, steady drip of methane hydrate dissociation, ice-like deposits of methane and water that stabilize seafloor sediments. As the last ice age ended and oceans warmed, these hydrates melted, turning the seafloor into a slippery, unstable slurry. The parallels to today are unnerving. Modern warming is already destabilizing methane hydrates along Arctic shelves, with sonar surveys revealing new gas plumes and pockmarks where the seafloor is collapsing. In some areas, like the East Siberian Arctic Shelf, methane releases have increased by 50% in just 2 decades. But here's the twist: tsunamis aren't the only threat lurking in these sediments. When methane bursts from the seafloor, it doesn't just destabilize slopes, it turbocharges global warming. Methane is 80 times more potent than CO2 over 20 years, and a Asteroid-scale release could pump billions of tons into the atmosphere. The geologic record shows this has happened before. 55 million years ago, the Paleocene-Eocene thermal maximum saw methane hydrates release en masse, spiking global temperatures by 8 degrees Celsius. The Asteroid sands are a tiny echo of that older catastrophe, a reminder that seafloor collapses aren't just local tragedies, they're climate grenades with the pin already pulled. Yet there's a sliver of hope in this soggy apocalypse. Unlike earthquakes or asteroids, underwater landslides give warning signs. Modern sensors can detect subtle shifts in seafloor pressure or methane seepage, giving coastal nations days or even weeks to prepare. Norway, for instance, now monitors its continental shelf with an array of seismometers and remotely operated vehicles, watching for the telltale shudders of sediment on the move. Even the tsunami sands themselves are teachers. By mapping their ancient paths, scientists can predict which coastlines are most vulnerable today. So the next time you walk a Scottish beach or hike a coastal bluff, look down. That unassuming layer of sand isn't just geology, it's a time capsule from the day the ocean fought back. And as the planet warms, its message couldn't be clearer: the seafloor remembers. The question is, will we, Washington's channeled scablands, look like something from another planet? A vast, scarred landscape of towering basalt cliffs, gaping potholes, and dry waterfalls so massive they dwarf Niagara. But the most jaw-dropping feature of all, Dry Falls, a crescent-shaped cliff 3 miles wide and 400 feet tall, standing silent and waterless. This isn't just a relic of slow erosion. It's a fossilized scream from Earth's most violent flood, a catastrophe so powerful it reshaped an entire region in days. Picture this: 15,000 years ago, an ice dam taller than the Empire State Building held back a glacial lake the size of Lake Michigan. Then it failed. The collapse unleashed a wall of water moving at 60 miles per hour, carrying 10 times the flow of all modern rivers combined. The flood didn't just carve channels, it gutted the landscape, plucking house-sized boulders from the bedrock and grinding them into tools that chiseled the cliffs we see today. Dry Falls wasn't dry back then. It was the epicenter of a waterfall 4 times taller than Niagara, with a roar that would have deafened anything within miles. The evidence is written in the rocks. Unlike normal river canyons which curve smoothly, the scablands are jagged and abrupt, with coulees, steep-walled canyons that end suddenly, as if the water simply vanished mid-flow. Giant ripple marks some 30 feet high and spaced hundreds of feet apart streak across the desert floor like frozen waves. These aren't the gentle undulations of a slow current. They're the footprints of a hydraulic monster, formed when the flood's turbulence dragged entire dunes of gravel across the land in minutes. Even the basalt columns, which normally weather into tidy hexagonal shapes, are shattered into chaotic piles, their fractures telling the story of water moving with enough force to peel rock apart. What's chilling is how fast it all happened. Geologists estimate the main flood lasted less than a week, perhaps as little as 48 hours. In that time, it stripped away 200 cubic miles of soil and rock, sculpting a terrain the size of New Jersey. The scale is almost incomprehensible. The flood's peak discharge was 10 times the Amazon River's current flow, with enough power to roll boulders the size of school buses like marbles. And it wasn't a one-off. Similar outbursts happened dozens of times as the Ice Age waned, each one adding another layer of devastation. But here's the twist. The scablons weren't recognized as flood scars until the 1920s. Geologist J. Harlan Bretz faced ridicule for his outlandish theory that a single deluge could carve such features. His peers insisted erosion was always slow and gradual until aerial photography revealed the truth. The land wasn't shaped by patient rivers, it was lashed into submission. Bretz's vindication revolutionized geology, proving that catastrophes could rival slow processes in shaping Earth. Now consider the modern parallels. Glacial lake outbursts still happen today, from Iceland's Jökulsárlóns to the Himalayas, where melting glaciers threaten communities downstream. And as climate change accelerates ice loss, the risks grow. The scablons are a warning. Water is the quietest architect of apocalypse. It doesn't just erode. It erases, yet there's beauty in this violence. The scablon's stark canyons and sun-bleached cliffs are now a sanctuary for rare plants and animals adapted to the harsh terrain. Even dry falls, though silent, hums with life, its plunge pool transformed into an oasis like Cooley where desert wildflowers bloom. The flood didn't just destroy. It created, and in its aftermath, it left a lesson etched in stone. Sometimes the most breathtaking landscapes are born from the planet's angriest moments. So the next time you stand on a riverbank, listen closely. The water might seem tame, but Earth remembers its fury, and the scablons are its monument, a reminder that when the planet decides to rewrite itself, it doesn't bother with a pencil. It uses a chainsaw. 2.5 million years ago, while early humans were just beginning to walk upright, a cosmic bullet struck Earth with terrifying precision, not on land but in the frigid waters off Antarctica. Today, hidden beneath the Southern Ocean's churning waves, the Eltanin impact crater tells a chilling story of near-miss annihilation. This submerged scar, spanning over 20 miles wide, marks where a mile-wide asteroid slammed into the planet with enough force to vaporize billions of gallons of seawater and send tsunamis circling the globe. But here's what's truly unsettling. Had this space rock veered just slightly north, striking a continent instead of the ocean, the course of human evolution might have been erased before it even began. Dredging up sediment cores from the crater's vicinity reveals traces of cosmic violence, tiny glass spherules forged in the impact's heat, mixed with iridium-rich dust that rained down for centuries afterward. The real smoking gun, though, lies in the layers of disrupted marine fossils. Microscopic plankton species that thrived before the impact vanish abruptly in the sediment record, replaced by hardier survivors in the aftermath. This wasn't just a bad day for ocean life, it was a planetary-scale shockwave. Computer simulations suggest the strike triggered megatsunamis towering over 600 feet, racing across the Pacific at jetliner speeds. Coastal ecosystems from South America to Australia would have been scoured clean in hours, their shorelines reshaped by waves carrying enough energy to pulverize coral reefs into sand. Yet the Eltanin impact's deadliest legacy might be what it didn't do. Unlike land strikes, which blast sun-blocking debris into the atmosphere, an ocean impact's effects are paradoxically both more localized and more insidious. The asteroid vaporized enough water to inject vast amounts of steam into the stratosphere, a greenhouse gas that could have amplified global warming for decades. Meanwhile, the sudden acidification of seawater from vaporized sulfur compounds may have triggered a marine die-off rivaling the worst mass extinctions. But crucially, the lack of continent-sized firestorms or decades of nuclear winter allowed land ecosystems and our fragile ancestors to persist. This cosmic roll of the dice raises a haunting question: how many other ocean impacts have we missed? Earth's seafloors are far less explored than the Moon's surface, and craters like Eltanin erode faster underwater. Recent sonar mapping has revealed similar structures off Norway and Canada, hinting that oceanic strikes might be frighteningly common. What's worse, an Eltanin-sized asteroid hitting today's warmer oceans could be catastrophic. Warmer surface waters would intensify hurricane-force steam explosions, while already stressed marine ecosystems might collapse under acidification. The Eltanin crater isn't just a relic, it's a mirror reflecting two futures, one where luck placed the bullseye in open water, and another where it didn't. As we scan the skies for asteroids, its lesson is clear sometimes. Survival isn't about preparation, it's about geography, and the next time the cosmos takes aim, we might not be so lucky. Beneath the jagged peaks of Namibia's Otavi Mountains lies one of Earth's strangest chemical paradoxes, a layer of pristine white limestone draped like a burial shroud over rocks scarred by glaciers. These so-called cap carbonates shouldn't exist. Limestone forms in warm, shallow seas, yet these sit directly atop deposits from Snowball Earth, the planet's most extreme ice ages. The transition is so abrupt it defies logic, mile-thick ice sheets vanishing overnight, replaced by oceans so warm they precipitated limestone globally. But this isn't just a geologic oddity. It's a cautionary tale written in stone, revealing how Earth's climate can lurch from freezer to furnace in the blink of geologic time. The secret lies in the chemistry. During snowball phases, volcanic CO2 built up in the atmosphere with no oceans or rain to absorb it. Over millions of years, concentrations soared to 10,000 times modern levels, a greenhouse gas bomb waiting to detonate. When the ice finally retreated, the planet didn't just warm, it boiled. Global temperatures spiked to 50 degrees Celsius, turning the poles into tropical swamps. The oceans, suddenly exposed to this CO2 deluge, turned corrosive as carbonic acid dissolved into seawater. But here's the twist: that same acidity triggered a chemical chain reaction. As calcium-rich glacial runoff met the acidic ocean, it neutralized the water in a violent spasm of limestone precipitation. The result: those eerie cap carbonates, global sheets of rock recording the precise moment Earth swapped ice for acid. What's haunting is how closely this ancient crisis mirrors our own. Today's CO2 spike is unfolding hundreds of times faster than snowball rebound. But the mechanics are identical: carbon overloading the atmosphere, acidifying oceans, and scrambling ecosystems. Fossilized algae in cap carbonates even show deformities akin to modern plankton stressed by acidification. The difference: neoproterozoic life was microscopic and resilient. Coral reefs and shellfish today have no such luxury. Yet within this catastrophe lies an even stranger clue: negative carbon isotopes. cap carbonates often show bizarre chemical signatures indicating something sucked CO2 out of the air as they formed. The likely culprits, cyanobacteria, exploding in blooms so vast they reversed the very greenhouse effect that birthed them. It's a reminder that Earth systems have emergency brakes, but they engage too late to prevent collateral damage. Now, the Ottavi cap carbonates are more than geologic curiosities. They're time capsules from a planet pushed to the brink and back. As we pump CO2 into the skies, these ancient rocks whisper a warning: climate recovery isn't gentle. It's a chemical riot, and we're the ones holding the match. Beneath Greenland's vast ice sheet, a monstrous scar hides in plain sight: the Hiawatha crater, a 19-mile-wide gash in the Earth's crust so fresh it might still smell of burnt rock. Discovered in 2018 by radar scans, this colossal pit wasn't carved by ancient tectonic forces or some slow geologic whim. It was blasted into existence by a half-mile-wide asteroid, a cosmic bullet that may have struck as recently as 12,000 years ago, a heartbeat in planetary time. What's chilling isn't just the crater's size, but its youth. If confirmed, this impact didn't just shake the ice, it may have shaken human history. The evidence is written in the ice itself. Unlike older craters worn smooth by millennia of erosion, Hiawatha's rim is jagged, its bowl-shaped depression still perfectly defined beneath the glacier. Radar images reveal rocky debris scattered around the site, including shocked quartz grains, those telltale fractures that only form under asteroid-scale pressures. But the real smoking gun, a layer of platinum-rich dust found in Greenland ice cores dating to the same period, a cosmic fingerprint matching the crater's suspected age. This wasn't a gentle touchdown. It was a fireball that vaporized thousands of tons of rock, scattering heavy metals across the atmosphere in a veil toxic enough to poison ecosystems worldwide. Now rewind to 12,000 years ago. Humans were spreading across North America, hunting mammoths and mastering fire. The climate was thawing from the last ice age until suddenly it wasn't. The Younger Dryas period hit like a hammer blow, plunging the planet back into glacial conditions for over 1,000 years. Traditional theories blamed melting ice sheets disrupting ocean currents, but Hiawatha offers a darker alternative: an asteroid impact so violent it triggered the freeze. Imagine the aftermath: wildfires raging across continents, sunlight dimmed by soot and debris, temperatures plummeting as the skies turn to poison. The crater's location under Greenland's ice sheet only amplifies the horror. A strike here wouldn't just throw dust into the air. It would melt trillions of tons of ice in an instant, flooding oceans with fresh water and shutting down the heat-toting currents that keep Europe and North America temperate. But here's where the plot thickens. The Hiawatha impact coincides with the disappearance of the Clovis people, a sophisticated Paleolithic culture whose spear points vanish from the archaeological record right around this time. Nearby, in the black mat layer we discussed earlier, mammoth and saber-toothed cat fossils pile up beneath a blanket of soot and nanodiamonds. The pieces fit a cataclysmic puzzle: an asteroid strike, a climate U-turn, and a wave of extinctions, all while humans struggle to survive. Some researchers even speculate that Hiawatha could be the second impact from a fragmented comet, with the first fragment triggering the Younger Dryas and the second, smaller but deadlier, landing in Greenland. Yet skepticism lingers. Crater dating is notoriously tricky, and some scientists argue Hiawatha could be much older, its youthful appearance a trick of ice's preservative power. Others question whether an impact this recent would have left clearer traces in global sediment layers, but even the doubters admit, if the timeline holds, it rewrites our understanding of human resilience. Our ancestors didn't just endure ice ages and famines. They may have stared down a cosmic firestorm and lived to tell the tale. The real lesson of Hiawatha isn't just about the past. It's about blind spots. For decades, we assumed major impacts were rare in human timescales. But craters like this, hidden under ice, jungle, or ocean, hint that the cosmos might have taken more potshots at us than we realized. As climate change melts Greenland's ice, who knows what other scars we'll find? Because here's the truth, Earth doesn't just keep its secrets in rocks. Sometimes they're buried in plain sight, waiting for the ice to crack. Buried in the layers of rock and sediment that will one day tell Earth's story, there's a whisper of us humanity's indelible mark, pressed into the planet like a fingerprint in wet clay. Future geologists won't need to dig deep to find our chapter. It's already here, a thin, global stripe of our own making, packed with clues so unmistakable they'll read like a manifesto. Plutonium-239 from nuclear tests, microplastics woven into ocean sediments, and a staggering volume of concrete, enough to blanket every inch of Earth's surface in a layer 2 millimeters thick. This is the Anthropocene, the epoch where humans became a geologic force. But the real question isn't whether we've left a record, it's what that record will say about us. Will it be a cautionary tale of collapse or the opening lines of a story about resilience? Take plutonium first. This radioactive metal, absent from Earth before 1945, now laces sediments from the Arctic to the Antarctic. Its half-life of 24,000 years means it'll outlast pyramids, cities, even languages. Future scientists won't just find it, they'll date our era by it, using its sudden appearance and decline after nuclear test bans like a geologic stopwatch. But plutonium isn't alone. Fly ash from coal plants, lead from gasoline, and the synthetic nitrogen choking our soils. All these form a chemical signature unlike anything in Earth's 4.5 billion year history. It's as if the planet's geologic code has been hacked, rewritten by a species that learned to reshape elements themselves. Then there's the plastic. Microscopic fragments now drift to the seafloor like artificial snow, forming layers that'll fossilize into permanent strata. In coastal areas, geologists of the distant future might find plasticrust, a disturbing new rock type where melted polymers bond with natural stone. Even more haunting are the technofossils, durable human-made objects like cell phones or car parts that could persist for millions of years, outlasting most biological remains. These aren't just relics, they're tombstones marking the moment consumption outpaced consequence. Yet the Anthropocene layer isn't just a dirge. Woven into its chaos are threads of hope. Urban soils, enriched by compost and green spaces, show unexpected biodiversity. Reforestation projects are sequestering carbon in ways that'll leave visible traces. Even our attempts to clean up, like the ozone layer's gradual recovery, could leave chemical repair signatures in ice cores. The Anthropocene might not be an epitaph. It could be a palimpsest, a document where our mistakes are scribbled over by corrections, adaptations, and hard-won wisdom. The most profound message in this layer, though, isn't in the rocks. It's in the choice it represents. Right now, the Anthropocene reads like a crisis, but it doesn't have to end that way. The same ingenuity that filled strata with plastic and plutonium could fill them with stories of restoration. Future geologists might sift through our layer and marvel not at our recklessness, but at our turnaround the moment we looked at the mess we'd made and decided to rewrite the ending. The Anthropocene is still being written, and the next line, that's up to us.